Action.
We hypothesized that Hi, I'm Natalie, and in this video, we explain how we experimentally determine the K-value of a spring.
What's a K-value?
I'm glad you asked, attentive student. So the spring constant, otherwise known as the K-value, is a physical property of springs, and each spring has its own unique spring constant. And another way to describe it is it's the amount of force needed to stretch a spring. So we found the spring constant using two different methods, and one was using simple harmonic motion and the period of oscillation, and the other was using Hooke's law and the displacement in the y direction. We expect that both methods will give us a similar result.
So we split this procedure up into two different methods. For method one, we're using simple harmonic motion. To do this, we added mass to the spring and pulled the spring down and released to create an oscillation. We measure the time it takes for the spring to complete 5 oscillations, and from there we can calculate period. So for method 2, we used Hooke's law. First, we measured the equilibrium position of the spring. Next, we added mass to the spring. From there, we measured the new length of the spring, which you could subtract the equilibrium position from and get delta y.
Okay, so for the Hooke's law data, what we did was we measured the change in position from the equilibrium and we compared it to the mass that we added. And this data table shows all the values that we got, and we had a nice little function through some algebraic manipulation in which we could determine the K-value as the slope of the graph, and we calculated our K-value for this data to be 3.436 newtons per meter. For the simple harmonic motion data, we recorded the period of the oscillation and we compared it to the amount of mass that we added. And this is our data table for all the points that we recorded. And we use this function here to compare period to the mass added, and through some algebraic manipulation we were able to figure out the spring constant, which for this data set we got to be 3.906 newtons per meter. In order to test our hypothesis, we decided to calculate the percent difference between our two values. So for simple harmonic motion, we got 3.906, and for the Hooke's law, we got 3.436. And using this percent difference equation, we were able to calculate a 12.81% difference between the two values. So in conclusion, we expect that most of the error from our experiment is derived from the fact that as humans, we don't have the best reaction time and we can't stop a timer exactly when we see something. So it makes our values for the simple harmonic motion a little bit skewed. And for the percent difference, it's actually not really that bad. A 12.8% difference really, for the fact that we're timing by hand, is not that bad.
So an interesting observation that we had was that the amplitude does not affect the period. And so what that means is that even if you pull the mass more, it doesn't mean that the period will change, because although it's moving faster, it also has to travel a greater distance. And if you look at the equation, you can see that even mathematically, amplitude does not come into play in the equation.
So relating this all back to why we would want to find the K-value in the first place, it turns out that spring constants are actually pretty important in real-life applications. They're used to model different scenarios, such as bonds between atoms. Thanks for watching!